Hello students, in this video we will derive the general equation for LC oscillators. The figure 1 shows the general form of LC oscillator. It comprises of amplifier section and feedback network. As we discussed in the previous video, LC tank circuit forms the feedback network in all LC oscillators. And an amplifier, BJT, FET or operational amplifier can be used as an active device. The input is applied between the terminals 1 and 3 and output is taken across the terminals 2 and 3. The output of the amplifier feeds the feedback network which consists of the impedances Z1, Z2 and Z3. The amplifier provides 180 degree phase shift while the feedback network provides an additional phase shift of 180 degree so as to satisfy the required condition for oscillation. Depending upon the type of reactances used in the feedback network, LC oscillators are classified into Hartley oscillator, Colpitts oscillator and Clapp oscillator. If Z1 and Z2 are inductors and Z3 is a capacitor, then the type of LC oscillator is called as Hartley oscillator. In Colpitts oscillator, Z1 and Z2 are capacitors and Z3 is an inductor. And in Clapp oscillator, Z1 and Z2 are capacitors and Z3 is an inductor series with the capacitor. This is the equivalent circuit of the general form of LC oscillator. Here the amplifier is replaced by its hybrid equivalent model in which the input impedance HIE and forward current gain HFE are taken into account. The reverse voltage gain HRE and output admittance HOE are neglected for analysis. Now let us start deriving the general expression for LC oscillator. Here in the input side we can see the impedance Z1 is connected in parallel with HIE. The parallel combination of Z1 and HIE is given by Z1 HIE divided by Z1 plus HIE and it is named as Z'. Next we will find out the load impedance ZL by looking between the terminals 2 and 3. To find out this, let us find the equivalent impedance of this network. The parallel combination of Z1 and HIE, that is Z' is connected in series with Z3 and this series combination is connected in parallel with Z2. This is represented in this diagram. Here, the Z2 is connected between the terminals 2 and 3. Z3 is connected between the terminals 1 and 2 and Z' is connected between the terminals 1 and 3. Here we can see the impedance Z3 and Z' are connected in series which is Z3 plus Z' and this series combination is connected in parallel with Z2. By looking from this side we will write 1 by ZL is equal to 1 by Z2 plus 1 by Z' plus Z3. Now we will replace Z' by Z1 HIE divided by Z1 plus HIE. Now let us take the LCM for this term. So it becomes Z1 HIE plus Z3 into Z1 plus HIE divided by Z1 plus HIE. This comes in numerator. Now we will bring Z3 inside. So it becomes Z3 into Z1 plus Z3 into HIE. There is no change in this first term. This is carried over here and in this part we will take HIE commonly out between the first term and last term. So it becomes HIE into Z1 plus Z3 plus the second term comes as it is. Now we will take LCM for this expression. So this becomes 1 into this term plus Z2 into Z1 plus HIE divided by Z2 into the denominator of the second term. Now let us bring this Z2 inside. So it becomes Z2 into Z1 plus Z2 into HIE divided by the denominator. We'll take HIE commonly out between this first term and last term. So it becomes HIE into Z1 plus Z3 plus Z2 plus these two terms are written as it is divided by the denominator. And this expression is equal to 1 by ZL. We know ZL is the load impedance. So we have to take inverse of this expression. Now the numerator becomes denominator and the denominator becomes numerator. This is the expression for load impedance. Next we will find out the amplifier gain A and feedback factor beta. Then we will equate A beta equal to 1 to satisfy the required condition for oscillation. We know that the voltage gain without feedback for common emitter amplifier is denoted by AV, which is equal to minus HFE by HIE into ZL. This negative sign indicates that the amplifier produces 180-degree phase shift. Next we will find out the feedback factor beta, which is defined as the output voltage of the feedback network Vf divided by the input voltage of the feedback network V0. We know that the output voltage is appeared across the terminals 2 and 3 and feedback is applied between the terminals 1 and 3. And this is represented in this diagram here. Now we will find out the voltage across the terminals 1 and 3, which is the feedback voltage, by using the potential divider network. So this Vf is given by the total voltage V0 into this impedance Z dash divided by the sum of the impedances Z dash plus Z3. Now we'll bring this V0 to the other side. So it becomes Vf by V0 is equal to Z dash by Z dash plus Z3. This is equal to the feedback factor beta. Now we will replace the Z dash in numerator and denominator by Z1 HIE divided by Z1 plus HIE, which we have found in the earlier part of this video. Now let us take the LCM for the denominator. So it becomes Z1 HIE plus Z3 into Z1 plus HIE divided by Z1 plus HIE. The numerator is written as it is. Now this Z1 plus HIE and this Z1 plus HIE are getting cancelled. We'll take HIE commonly out between the first term and last term of this denominator. So it becomes HIE into Z1 plus Z3 plus Z1 Z3. The numerator is Z1 HIE. This is the expression for beta. For sustained oscillations, we know AV beta equal to 1. Let us substitute the expressions for AV and beta. This is the expression for AV and this is the expression for beta. Both we have substituted in this expression. We can see the denominator of the first term and this HIE are same, so they are getting cancelled. Now we will replace ZL by this expression which we have found in the earlier part of this video. Now this portion of this first term and the denominator of the second term are same, so they are getting cancelled. So we will write minus HFE Z1 into Z2 divided by this term as the denominator is equal to 1. We'll do the cross multiplication. So it becomes 1 into this term is equal to this term is equal to minus HFE Z2 Z1. We will bring this minus HFE Z1 Z2 in the left hand side. So it becomes plus HFE Z1 Z2 is equal to 0. Let us take Z1 Z2 commonly out between the second term and the last term. When it is taken out, it becomes Z1 Z2 into 1 plus HFE plus the remaining terms are written as they are. This is the general expression for LC oscillator. This is used to find out the frequency of oscillation and condition for oscillation for all three LC oscillators, which are Hartley oscillator, Colpitz's oscillator and Clap oscillator. Thank you.